So, having discussed the properties of Fourier series, in particular the exponential Fourier series and the trigonometric Fourier series, uh, over the last few lectures, and identifying the reason of representing the signals in that particular form, now we are in a position to calculate the Fourier series expressions for some of the very useful signals under consideration. So to start with, let us consider one continuous time signal which looks something like that. Let's have a signal which looks something like that. This is the time axis. And this stands for t is equal to 0. And we have a periodic square wave. A periodic square wave with a time period given by, say, capital T. So therefore, this value is equal to t is equal to minus t. This value stands for t is equal to plus t, and this corresponds to t is equal to, let it be t0 by 2. This value corresponds to t is equal to minus t0 by 2. So what we find is that this particular square wave, so it continues towards the positive time axis in this direction, and this continues towards the negative time axis. And suppose this height is equal to unity everywhere. This is 1, this is 1, this is 1. So this is a perfect example of continuous time periodic signal, a square wave signal, which is having a time period of capital T. After every t it gets repeated, and from minus t0 by 2 to plus t0 by 2, for this one we have a square wave pulse, something like that. So this particular signal can be represented mathematically like this: x of t is equal to 1 for minus t0 by 2 less than equal to t less than equal to t0 by 2. If I just consider this particular thing, and that is equal to 0 otherwise, 0 otherwise. And we also note that x of t is equal to x of t plus capital T. That is true for all t. So it's a periodic waveform, periodic square wave, which is having a value like that, and we are in a position to represent the corresponding Fourier coefficients from that particular x of t. So we know the formula for calculating the Fourier series. Actually, the formula goes something like that: x of t, since it's a continuous time signal, so we can write something like that: x of t summation going from k is equal to minus to plus infinity x of k. Then we have e to the power j k omega naught t. That is the Fourier series expression. And how to find out the corresponding Fourier coefficients x of k? That Fourier coefficients x of k, I think we can shift it over there. This Fourier coefficient x of k can be represented as 1 by t, that is the time period, integration over 1 period. So that integration is over one period. Since here the signal is existing from minus t0 by 2 to plus t0 by 2, so you can also write it down from minus t0 by 2 to plus t0 by 2. This integration has to be calculated over a single period. Then x of t e to the power minus j k omega naught t dt. What is omega naught here? This omega naught is equal to twice pi by capital T. So that is the generic expression. Now we are in a position to calculate the value of this x of k for different values of k. So this x of k can be represented as 1 upon t integration over. In fact, over here I have written like minus t0 by 2 to plus t0 by 2 because the signal exists from minus t0 by 2 to plus t0 by 2. Typically, you can write it from minus t by 2 to plus t by 2, but from minus t by 2 to plus t by 2, the signal doesn't exist. Signal only exists from minus t0 by 2 to plus t0 by 2. So that's why I've written like that. If you wish, if you're very much particular, you can also make a small change over there. Instead of writing or instead of going for a step jump, you can also write something like that. 1 by t minus t by 2 to plus t by 2. But you note that from minus t by 2 to minus t0 by 2, the signal is 0. And from t0 by 2 to t by 2, the signal is again 0. So therefore, we can only integrate from minus t0 by 2 to plus t0 by 2. So therefore, this is minus t by t0 by 2 to plus t0 by 2. Signal value is x of t, then e to the power minus j k omega naught t. That is equal to 1 by t integration minus t0 by 2 to plus t0 by 2. X is equal to 1, so e to the power. So we should have a dt over there. E to the power minus jk omega naught t dt. So that is equal, if we integrate this one, e to the power minus jk omega naught t dt, that will give us 1 by minus j k omega naught capital T, then e to the power minus j k omega naught T. The value should be placed from minus t0 by 2 to plus t0 by 2. Now, one thing you have to notice over there, whenever I write this expression, so in that case, there is a k in the denominator. So this x of 0 value will become undefined. So that's why this particular expression is valid for k is not equal to 0. And we'll calculate how to find out the value of x of 0. So we calculate the all xk value ranging from 1 to up to infinity and from minus 1 to minus infinity. But only for k equal to 0, this is not defined. And you know how to calculate it for xk equal to 0. And that gives you the average value that you have considered in the last class. So that is equal to e to the power j k omega naught t naught by 2 minus e to the power minus j k omega naught t naught by 2 divided by jk omega naught t. Okay. Now what is this omega naught? This omega naught is equal to 2 pi by capital T. So therefore, you can also substitute this value like this. E to the power j k. So omega naught by 2 will give you pi by t. Then e to the power jk pi t naught by t minus e to the power minus jk pi t naught by t divided by, you have j there, k there, omega naught will give you 2 pi by capital T. So we have like 2 pi only. Omega naught t is equal to 2 pi. It is by jk 2 pi. So we can further simplify this one. E to the power jx minus e to the power minus jx by 2j will give us the value like sine, as you know, sine x. E to the power jx minus e to the power minus jx by 2j. So what you have jk pi t naught by t, and then e to the minus jk pi t naught by t. So we can simplify this one. Let's go to the next slide. The value for x of k, this x of k is given by, in the denominator what you have, the denominator we have jk 2 pi jk 2 pi, and in the numerator what we have is e to the power j k pi t naught by t, e to the power j k pi t naught by t minus e to the power minus j k pi t naught by t. So we can write in this way: e to the power j k pi t naught by t minus e to the power minus j k pi t naught by t e to the power jx minus e to the minus jx by 2j. That will give the sign component. What is left? K pi is left there. So that is equal to 1 by k pi sine of k pi t naught by t. So this can further be represented in this particular form, a special type of function which is very much popular in the field of signals and systems, that is k pi t naught by t. Then we have already k pi there, and then you have t naught by t, that gives rise to, so we need to multiply it with t naught by t. This particular function is known as sin c function. So t naught by t, then we have sin c of k t naught by t. Let's review it once again. The signal variation is from minus t naught by 2 to plus t naught by 2. So we write something like that: x of t e to the power minus j k omega naught t dt. The integration has to be carried out over the entire period, that is capital T. So if we just integrate this one e to the power minus j k omega naught t, that will give us 1 by this one minus j k omega naught capital T, and then you have e to the power minus j k omega naught t. T is ranging from minus t by 2 to plus t by 2. So that will give us e to the power j k omega naught t naught by 2 minus e to the power minus j k omega naught t by 2, and omega naught is given by twice pi by the total time period, that is capital T. So if you simply substitute this value, you have like e to the power j k omega naught is represented by 2 pi by t there. Okay, so omega naught is represented by 2 pi by t. So omega naught by 2 will give you pi, that's fine. So e to the power j k pi t naught by t minus e to the power minus j k pi t naught by t, and we have like k omega naught t will give us jk2 pi. So e to the power jk pi t naught by t minus e to the power minus jk pi t naught by t divided by jk2 pi. So e to the power jx minus e to the power minus jx by 2j will give us the sine function. So that is equal to 1 by k pi sine k pi t naught by t, and then what we have 1 by k pi multiplied with sine k pi t naught by t divided by k pi. Now this argument has to be made same in the denominator also. So k pi t naught by t divided by k pi t naught by t naught by t is the extra term that I have to multiply with the numerator as well as with the denominator. So ultimately what we get is t naught by t sin c k t naught by t. So sin c is a special type of function in signals and systems which is having a property something like that: sin cx or sinc function, that is equal to unity for x equal to 0, and that is equal to 0 for all integer value of x. For all integer value of x. So basically a decaying function. So what we have ultimately, x of k is given by t naught by t sin c k t naught by t. And you can also plot this one. Now that particular expression has been formulated for all values of xk excluding k equal to 0. So for k equal to 0, we can straight away find out the expression, this x0 value, the dc value. The dc value is given by 1 by t integration for the entire period minus t naught by 2 to plus t naught by 2 x of t dt. We just put k equal to 0. The expression was like x of k is equal to 1 by t integration from minus t naught by 2 to plus t naught by 2 x of t e to the power minus jk omega naught t dt. Just simply put k equal to 0, e to the power term gets vanished. What we have is only x of t dt, and from minus t by 2 to plus t by 2 the value is equal to unity. So it gives rise to t naught by, so ultimately this is 1 by t integration from minus t naught by 2 to plus t naught by 2 dt. So t naught by 2 minus or minus t naught by 2, that will give us t naught. So t naught by t. And that gets satisfied over there. So x of k, if you just take a look at this particular expression, there you find x of k is equal to t naught by t sin c k t naught by t. So when k tending towards 0, if I apply L'Hospital's rule, when k tending towards 0, this sin c function, when x tending towards 0, then the sin c function will give us 1. So ultimately, the value becomes t naught by t. So it gets satisfied. So ultimately, how does it look like, the ultimate signal in the frequency domain? So we have, remember, this x of k is defined only for the integer values for k. So this is k. Start with k is equal to 0. Then you have the other values. And basically, what we have for k is equal to 0, what I get for k is equal to 0, the value is equal to simply t naught by t. And then for, if I consider k is equal for all integer values of x, that means integer values of x. So when k t naught by t is equal to 1, then once again it becomes 0. So for k t naught by t is equal to k t naught by, because that is the argument, k t naught by t is equal to plus minus 1, plus minus 2, and so on, plus minus 3, and so on, the value becomes 0. So had this been the case, then it suggests that k should be equal to at plus minus t by t naught plus minus 2t by t naught plus minus 3t by t naught, the value will be 0. So accordingly, we have to identify those values, and then the variation, although I'm showing a continuous kind of variation, but remember this is a discrete variation. So when k is equal to plus minus t by t naught, so suppose this is the value, this is the value, there you find, say, suppose this is minus t by t naught, this is say plus t by t naught for k, this is say 2t by t naught, this is say minus 2t by t naught, then you have like 3t by t naught, then you have minus 3t by t naught. So in these particular values for k, the x of k is equal to 0. So if I assume that, okay, t naught, this particular ratio t by t naught, as of now we have not assumed anything, but we can assume that, okay, t by t naught is equal to, say, let it be say 2. That means t naught is equal to is t by 2, right? So t by t naught is equal to 2. So this value will correspond to k is equal to 2. So over here you have these values. So now we can plot the values over there. That is assumption that suppose t naught is equal to t by 2, accordingly you can plot. So this is the first value corresponding to k is equal to 0. Then you have the second value. Here you have a decaying pulse over there, sinc function. The value can be anywhere in between. It's known as the first lobe. This value over here is the second value, k equal to plus 1, k equal to minus 1. Then you have k is equal to minus 2 there, k is equal to plus 2 there. Then you have k is equal to 3 there. Then k equal to 4 there. Then k equal to 5 there. Then k is equal to 6 there. And as you progress, the height of these side lobes, these are known as the side lobes. This is the main lobe, the first zero crossing from both of the sides of this k is equal to 0 axis, first zero crossing, and then you have the side lobes. And the height of the side lobes goes on reducing. Similarly, here also you have a variation like this. And this is symmetric with respect to k is equal to 0 axis. This is symmetric. So it looks something like that. So this is a particular typical sinc function which looks something like that. So now the bottom line is that, and if you just connect the dots, we can identify what should be the nature. How does it look like actually? But remember, the signal is continuous in the time domain. The actual signal that you have started with is x of t, that is continuous in the time domain. So now since it is continuous in the time domain and periodic obviously, so its frequency domain representation, the Fourier series that we have got, the Fourier coefficients are discrete in nature. X of k for all k ranging from minus to plus infinity, including k equal to 0. So that is the value for k equal to 0. Here you have this value, and this value is given by t naught by t, because this is t naught by t multiplied with sin c function. So this value should be t naught by t. This one, this is t naught by t, and accordingly you have the intermediate values. So this is the Fourier series representation of this kind of signal. Now sometimes the signal cannot be so simple. This is a very elegant function, a simple square wave signal, very elegant function to look into in the field of signals and systems. But there are certain situations where you have some combined functions. It's not as simple as like a square wave. Might be some modification, might be some addition of weighted addition of 2 or 3 known functions. It is one of the known functions, square wave. So suppose you are asked to find out the Fourier series representation of a signal, which is not simply a square wave signal, but it's a weighted summation of the square wave signal. Suppose, let me gradually go into some of the properties of the Fourier series representation. Suppose you know for x of t, if the signal is x of t, it's a periodic signal, then the corresponding Fourier coefficients are represented in the frequency domain like x of k. Simple Fourier series. Suppose you know y of t, it is another periodic signal of same period, same fundamental period, for which the Fourier coefficients are given by y of k. And suppose you are asked to find out the Fourier series coefficient of a signal which is having the form ax of t plus by of t. Now there are two provisions to calculate this one. Either you take the signal as it is, set t is equal to axt plus byt, find out the Fourier series coefficient directly, or you can also invoke the linearity property of the Fourier series representation. That is very, very useful. So what does it say? This linearity property, that if I know the Fourier series coefficients for x of t and y of t having the same period, then the Fourier series coefficients for the signal z of t is nothing but a times xk, sorry, this is small a times xk. That means we have invoked the additivity property as well as the homogeneity property. A times xk plus b times yk. So that reduces your job tremendously. So you are not going to calculate, you know, the Fourier series representation for some of the typical functions, most useful functions. One of the functions I've already shown, the square wave representation. And if you can represent, or if you can identify the signal zt as a weighted addition of the already known signals, popularly known signals, and you know the corresponding Fourier series representation of those signals, then you can very easily calculate the Fourier series coefficients of the compound signal without going into the details, and that is known as the linearity property. Linearity property of Fourier series. Now, if I just take a look at the expression for the Fourier series coefficient for any continuous time signal x of t, that is equal to, suppose the signal is a real signal, k is equal to minus 2 plus infinity x of k e to the power minus j k omega naught t. That is the Fourier series representation for any continuous and periodic signal. And let us also assume that the signal is a real signal. What does it mean? That means if I calculate the value, if I measure the value of x of t for any t, so that gives you real value. There is no complex number, only the real values are there. However, in this expression, if you just take a look at this expression, there you have some complex quantity to the power minus j k omega naught t, that is a complex term. So which implies, in order to make the left hand side real, this right hand side, this x of k has to be complex. It has to be complex. Otherwise, if xk these are real, then obviously real multiplied with complex cannot give you real in the left hand side. So remember that even if the signal x of t is a real signal, but the corresponding coefficients, Fourier coefficients, they can be complex as well, right? So therefore, there is another property. So as you know, we have like x of k, the values of x k from -1 to minus infinity, +1 to plus infinity, and then 0, the DC component. Now the symmetricity, so another property is there, symmetricity property, which allows us to calculate this x of minus k directly from x of k. And it can also reduce our job significantly. So for example, you know that this x of k is given by 1 by t integration over 0 to t x of t e to the power, sorry, there should be plus sign there only, so minus sign, this is plus, yeah, e to the power minus j k omega naught t dt. Now if I take the complex conjugate of this x of k, which gives us x star k, how can I write this for a real signal? 1 by t integration over 0 to t. So I can write like x star t there, and the complex conjugate of e to the power minus jk omega naught t will give us e to the power plus jk omega naught t dt. Now since the signal xt itself is real, so I can simply write like 1 by t integration over 0 to t, x star t will be xt, and there you have e to the power, I can write like this, minus j multiplied with minus k, then omega naught t dt. And this is nothing but x of minus k. This is nothing but x of minus k. So if the signal is a real signal, so for a real signal, if you can calculate the x of k, then finding out the value for x of minus k is pretty easy. It's very easy. You should not calculate x of minus k separately. Once you know x of k, take the complex conjugate of that. That will give us the value for x of minus k. On the other hand, if the signal, so that is for the real signal. So let me write it down over there. For a real signal. for a real signal xt. On the other hand, if the signal is an imaginary signal, for example, in that case, what happens? If the signal is an imaginary signal, so in that case, we can invoke the same thing. This x of k is equal to 1 by t integration over 0 to t x of t e to the power minus j k omega naught t dt. So now if I take the complex conjugate x star k, that is equal to 1 by t integration over 0 to t x star t e to the power j k omega naught t dt. Now for perfect imaginary signal, so there we have written for real signal xt, for real signal xt, for real signal xt is equal to x star t. That is obvious. But for imaginary signal, x star t is nothing but minus xt. So now if you just simply substitute this value over there, you have like minus 1 by t integration over 0 to t x star t will give us minus xt, so minus xt, then you have e to the power minus j, then the same procedure minus k omega naught t dt. That is nothing but minus of x of minus k. So if you have a real signal, then x star k is equal to x of minus k, and if you have imaginary signal, then x star k is equal to minus of x of minus k, and that is known as together, that is known as the symmetricity property. Symmetricity property of Fourier series. This is known as the symmetricity property of Fourier series. Fourier series representation.